Let's now take a quick look at corrosion, the degradation of materials due to electrochemical processes. Probably the most important reaction we could look at is that the corrosion of iron, because it is just such a common material. I don't know, maybe wood is used more than iron, but it's certainly way up near the top. And mitigating iron corrosion is a multi-billion-dollar a year industry. I knew folks in industry from my days there that they did nothing more than study corrosion their entire career. How to identify when it occurs, how to identify what makes it occur, and how to identify ways to mitigate corrosion. Well, what is corrosion? Well, essentially we have iron, and it can react to produce iron 2 by giving off 2 electrons in an electrochemically favorable reaction. Fortunately, it can't happen by itself. It needs something to actually donate electrons. It needs a cathode half cell. That's the good news. The bad news is that's normally readily available in the form of water, which has a lot of protons in it and which has dissolved oxygen. Granted, not much oxygen, but if you got a good pair of gill slits, you can get by with a few parts per million in water. And so the overall corrosion reaction is shown there at the bottom line, producing 1.67 volts. So let's look at that schematically, what happens. The degradation of iron occurs. You have iron that's in your metal. Once it donates electrons, it then becomes iron 2. And the problem is iron 2 is soluble in water. And it reacts with oxygen to make this material known as rust. And that in itself is not the problem. The big problem is rust has no structural integrity. And so you wind up with the metal just being degraded away. Is rust always bad? Not with aluminum. With aluminum, you form aluminum oxide, and aluminum oxide has good structural integrity. It actually protects the metal. And so in that case, it's a welcome. But with iron, not so much. Now, what happens to the electron that our iron releases? It then goes over and finds some oxygen and some protons in the water, and it reacts to form more water. And that completes your cycle. You have an anodic site and you have a cathodic site, and the net result is your metal gets eaten away. Well, how can we prevent it? There's 5 key ways I want to tell you about preventing it, and they're fairly straightforward. The first one is the use of filmers. And filmers are essentially chemicals that are placed into the water, and the water carries the long filmers, and they essentially plate out on the surface of the metal. And they offer protection in this manner. So, if oxygen can no longer get to the surface of the cathodic site, then this reaction is broken and corrosion does not occur. And you can imagine the same thing is true with the second, more obvious way to prevent corrosion, which is painting. Again, you paint something, it merely covers the surface and prevents this reaction from occurring. They don't paint battleships just to make them look pretty and gray. They paint them to protect the ship from the salt water. Next is a neutralizer. Now we're getting into the little bit of chemistry here. Now within this reaction we can see our protons are needed. And so you can put filmers called neutralizers in here, and essentially they're basic materials that are negatively charged, and they would just combine with the protons and make a compound and essentially scavenge those protons. And again, it stops the cathodic reaction. Those are 3 pretty simple ways. There's two more that get at the reaction of iron going to iron 2. And that's called galvanization. And you've heard of a galvanized nail, no doubt. And then one is called cathodic protection. Now what's causing all this problem is iron is being oxidized to iron ion. Now how could we stop that? Well, let's think about our basic chemistry that we've learned so far. If we had a metal that was more reactive than iron, then it would oxidize. It would be the thing that corrodes. And the iron would be left unattacked. So what we need is a metal that's more active. For example, one may see on battleships, actually I've seen pictures of them, where there's these huge kind of blocks that are just welded onto the side. They look like pretty clumsy patches. They're not patches. They're big pieces of zinc that are welded onto the side. Why? Because zinc is more active than iron. And so what one will get, instead of the iron donating the electrons, it will be the zinc that donates the electrons. And it's these zinc patches that will now corrode and not the iron. The last one I want to mention is galvanization. Making a galvanized nail is the most common example. And this is very similar to what we did on our battleship on the other side. We're going to mix a more active metal in the metallurgy than iron. And in that case, zinc is nice and cheap and it will do finely. So zinc is literally mixed in with the metallurgy and is that bit of zinc that corrodes and not the iron, thus protecting the structural integrity of the iron nail. And with that, that's your 5 ways to prevent corrosion: filmers, painting, neutralizing, galvanization, and cathodic protection.